and it's going to tell me that to tell everyone that you're being recorded, and this video will go up, or the recording will go up on Sunlearn. What else do I need to do? Messages and participants. Two more. Let's see how many people. 27, 28, 29, 30, 40. Oh, okay. So lots of students. More than ever come to class. That's not true. Right. A couple of announcements. One is that you must please remember that your projects are due on the 1st of June, which means you still have this weekend and next weekend, but then it's hand in time. There's also a demo schedule. You have to make appointments with a demi to to demonstrate your project, or a marker to demonstrate your project. And Nicole put up a list of slots, and I haven't checked how many people have filled that in, but please do that. I'll remind you again next week, all the time. Right, what else do I have to tell you? Let's see. Oh yeah, Wednesday's meeting. I'm so sorry. I apologize that we didn't have a chance to meet on Wednesday, but I'll be honest, I have a new fiber installation that's just a little flaky, and Wednesday morning it didn't work. But you watched those two videos about that Dr. Grobler recorded about the towers of Hanoi and also GCD. I am very behind with the videos that I promised you. After this, I have another class, and then I'll record last Friday's lecture finally. And I'll also record a couple of the live coding videos. I have one that I should just upload, and there are also the shorter videos. Once again, if there are topics you want me to talk about, let me know, and I'll make a video about that. But there's supposed to be short. I will make a couple about recursion, and I will add more quizzes. But this week has been crazy, cray, as the kids say. Also, yeah, no, sorry, that's fine. So that's, I think, all the announcements. I can't think of anything else. Please make sure that you submit the project ahead of time and double check that it's actually been uploaded. There's no takebacks like maybe for the first hand in. If you hand in an empty project, or you don't hand in the Java files, you won't get a second chance. Please make sure that they're done properly. I'm still sorting out the test dates, so I'm still waiting for our administration to tell me when I can make our test. It will be after or on the 8th of June, but there's only this one test remaining, and you have to write it. I mean, I talked to someone else this morning who said, do I really have to write this test? But it counts 32% of the marks, so you have about 68% marks already after you've handed in the project. But unless you scored 75% for all of those, you won't pass the course. And you're also taking a chance because you're just on the 50 cusp. So if anything goes wrong, you won't pass. So the test is critical. There is a third test, but that's only for people who have a medical certificate having missed either the very first test we wrote or the second upcoming test. If you're ill, or if you have a scheduling conflict, then you can write the last ditch test, but we'll schedule that at a later date once we know who has to write it. Sir, I've got an email saying I write the test on the 19th of June. Well, I haven't seen that, and I'll double check it, and I will fix the dates, but maybe only next week, because I didn't get that email. Okie dokie, so let's talk about recursion. There's one more exercise in the book we are going to look at. I'm just assuming that you understand towers of Hanoi and GCD and factorial. But let's look at this fourth example in the book. And if you're still in doubt, please let me know and I'll make some videos about it. But next week, we're going to do more recursion, but we're going to look at graphics, how recursion can be visualized in some sense. And it's a fascinating topic because you can do lots of stuff with recursion that you can't necessarily do without it. So I'm going to screen share first the textbook so we can have a little read of that. Okay, right. So this little example is called gray codes. Now, I don't think we've done it explicitly in class, but there have been one tutorial exercise called base jumping about expressing numbers in a base other than 10. We're so used to the decimal system, writing numbers with 0 to 9 digits, that we take it for granted. But there are other number systems like binary, which is what computers use. So if you look at a number like this, 0, 0, 0, 0, that represents 0. And if I add 1, I now have 1. This is the binary number 1. And if I add 1 to that, well, 1 and 1 is 2, but this is base 2. So just like in base 10, if you add 4 and 6, that doesn't become the digit 10. There is no digit 10. 4 plus 6 is 0, and we carry the 1 because we've gone over the base 10. So the 1 goes into the next column. So that's why 6 plus 4 has 2 digits instead of just 1. And in the same way, if I added 1 to 0, 0, 0, 1, 1 plus 1 is 2, but I'm going to write a 0 and carry the 1 over. And so the next number will be this. Let me just highlight it. I think I can. Can I? Highlight. Oh, that's not what I want to highlight. Let me just get the right tool. Text selection, annotate. Just 1 second. Highlight text. I thought I am highlighting text. Okay. Well, it's a textbook. It's not very clear, but I want to highlight this number here, the fourth one. That is what I get if I add 1. Okay, now it's all highlighted. That's. Oh no, this is all wrong. Can I undo this? Yes. So the first line is the number 0. This next line is number 1. The fourth line is the number 2. If I add a 1 to that, well, 1 plus 0 is 1. There's no carry. Then I get the number on the third line, which is 3. So I can carry on like this, and I can count in binary, just like I would have counted in decimal. But there's a thing about binary, and that is going from 1 to 2 means I have to change the first digit to a 0, and the second digit from a 0 to a 1. And in some situations, we don't want that. We want to change only one digit at a time. But we still want to list all the numbers. In this case, from 0 up to 8. And this is what this exercise is about. How do I take any number, any old number here, like 1100, and which digit should I change to get to the next number in this list? In this case, I change the first digit, then the second one, then the first one again, then the third one. So it's not exactly clear what digit I must change. The way this problem is framed is that they talk about Samuel Beckett and a play he wrote called Quad. And at any time, there is some actor on stage, and they're given numbers 1 to 4 in this case. And during the play, either an actor who is not on stage enters the stage, or an actor who is on stage leaves the stage. And at the end of the play, all possible combinations of players have been on stage, all possible subsets, and exactly once. So if we think about 1 and 2, they were only on stage alone. Only 1 and 2, that unique set of actors, was only on the stage at one point. And never again. I mean, 1 and 2 were there, but then they were either with 4 or with 3 or with 3 and 4. So there's only one instance in the play where 1 and 2 were on stage alone together. That subset of actors was on stage once. So how do we generate this list? And in this little program, how do we generate these instructions for the actors to enter the stage or exit the stage? In other words, how do we pick which digit to change? Firstly, they talk about 2 to the 4. Why do they do that? Well, if you look at each of the actors, they're either on stage or they're not. So there's a choice of 2 possibilities for each of the actors. If we say that this leftmost digit is actor 4 is either off stage or on stage. So there are 2 choices for 4, 2 choices for actor 3, 2 for actor 2, 2 for actor 1. And if we multiply those 2's together, 2 times 2 times 2 times 2, 2 times 2, yes, that's 2 to the 4th power, and it's 16 different combinations, 16 different subsets. This idea of labeling subsets of a set is very common in computer science. Okay, so now let's talk about how do we actually generate this list. And the textbook explains it with this diagram on the next page. It's beautiful because it analyzes these different patterns. And we see a clear pattern emerging, and that is that if I have, let's say, 3 actors, and I want to generate instructions for 3 actors, if I just cover the first digit and look at the second and third column, and I divide that by 2, I see that the first 4 list of digits is identical to the instructions I generated for 2 actors, 0001 1110. And here it is, 0001 1110. And the second part of this list is the same as the first part, it's just reversed. So if you can imagine, if I can go from 00 to 10, changing 1 digit at a time, taking or adding 1 actor at a time, I can go the other way as well. So I go up with a certain set of instructions, then I ask actor 3 to enter the stage, and I go back with the same instructions that I had when I organized the first 2 actors. And we can repeat this idea. If we look at 4 actors, if we cover the first column, if we ignore the first column, the second, third, and fourth column, the pattern that appears here is exactly the pattern for 3 actors, going from 000 to 100 and 000 to 100. Then actor 4 enters, and then we just go back in the reverse. So this is recursion in some sense. To generate the pattern for 5 actors, I would generate the pattern for 4 actors. I would say actor 5 enters the stage, and then I generate the pattern for 4 actors again, but this time just in reverse order. So how can we use this to write a recursive program? Let's think about this, and we'll look at the code in a second. So I'm asked to do 5 actors. I'm going to first call myself to generate the list for 4 actors, and then I'll say add this instruction, enter actor 5, and then I'm going to call myself again with the list for 4 actors, but this time I'm going to reverse it somehow. So let's look at how the code does this.
Right, at this point my audio was muted, so I'm going to try my best to explain from here for the next about 2 minutes. So this is the program we're looking at, but we're going to start looking at main. So main accepts a command line argument n, which is the number of characters or actors, and it calls moves. It passes true to indicate we're going first in the forward direction. The parameter of moves is called enter, but direction would have been, or forward would have been a better name for that. First we're going to repeat it for true and then for false. So we start off by saying that if there are 0 players, then we just return immediately, because there are no moves to generate. But if there are, if enter is true, we generate the forward moves for n-1 characters, and then we're going to handle the nth character, and after that we are going to call moves again recursively to generate the list for n-1 characters. Let's just see me highlight that. There we go. So those are 2 recursive calls for generating the forward list and a backward list. And in the middle, if we're going forward, the character enters. If we're going backwards, the character exits. I think that is what I was trying to explain here. So it's not that hard to understand. It's simply generating that list of grey codes we saw before. Okay, let's carry on.
Yaku, you're muted.
I'm so sorry. I don't know when I started being muted, but please don't press the mute button for me. The way that Teams work is that anybody can mute anybody else. So it's difficult for me to see that I am muted. I can just, this little microphone in the corner, so please don't mute me. So I was saying that you have to, when you use recursion, you have to believe in yourself in some sense, believe in your code. So once we define moves, we must believe that it will generate the list for n actors, either forwards or backwards. So that when we write the code and we call moves n-1 true, we don't have to think about it too deeply. We just assume that this will generate the list for n-1 actors forward, and this will generate the list for n-1 actors backwards, going in reverse. So it's very difficult, I know, especially if you're solving a problem you've never seen before. But there's this paradox almost that if you write a recursive routine, you must already believe that it will work correctly. I mean, I will give you an example of that right away. I'm going to stop sharing this textbook and I'm going to repeat this code in Eclipse. Let me just share again. I'm not muted yet. Good. Okay, right. So we're supposed to write back. I'm just going to repeat that code, but first I'll tell you what I mean by this believing in recursion. I want to write a routine called factorial that will generate the factorial for n. Now, I know that n factorial is n times n-1 times n-2 times n-3, but apart from the termination condition, where I'm going to write n is less than or equal to 1, we send back a 1, else. I must just believe that if when I call factorial n-1, that this will work correctly. This will actually calculate the factorial for n-1, which I can then multiply by n to get the factorial for n. So I trust myself that this is the factorial for n-1, and if that is true, then I know this whole routine will return the factorial for n. So I kind of have to trust that the recursion is working correctly. So let's just write the bracket, because I don't necessarily believe that it works. I want to see it. They call it moves, but I will call it directions, because it's stage directions. This is the number of actors. So I will say actor count. And then there is a Boolean, which is the direction. I'll just make this a little smaller that you can see. Right. So if the actor count is 0, there are no actors, and we don't have to issue any directions. Then I want to generate that forward list of directions that we looked at in the picture that says the pattern for n, or actor count, starts with the pattern for actor count minus 1. So generate the directions for actor count minus 1 in the forward direction. And I must just believe that this will work. And then I'm going to say, if we are in the forward direction, if direction, display enter, oh, can't spell enter actor count. And else he has, or she, or they have to exit. So this is the equivalent of switching on the 1 in the last column, and then I generate the directions for actor count minus 1 false. So all the directions again going back. And the example in the book read a command line parameter, but I will just go with, I'll go with 2 true. Just want to see how it works. If we run that, we get enter actor 1. So we start with the stage empty, that's a valid subset of actors. Actor 1 enters. Can I type here? No, so I'll type here. We start with empty, so that's 0, 0. Then actor 1 enters, 0, 1. Then actor 2 enters, so that's 1, 1. And then actor 1 exits, so that's 0, 1. So this looks correct to me. Firstly, it starts with this list where one actor goes forward, and then it's got this list where actor 2 is entered, and now the other actors go, the list goes backwards. So this 1, 0, I can't do that. I get, oh no, that didn't work very well. This 1, 0 is a reflection of 1, 0 at the top. Let's try it for 2 actors. Oh, sorry, 3 actors. We've done 2. Let's try 3. Oh, it's a much longer list. But what we should see is what we had for 2 actors, and then actor 3 enters, and then again 2 actors, but reversed. So here you can see that the 1 enters here, but here they exited, 2 exits, but there they entered, and 1 exits, but there he entered. I don't think this is the clearest example of recursion, but it emphasizes the fact that we must kind of believe in ourselves, like we did for factorial without even noticing it, and also like you do for GCD. When you write GCD, you just assume that the GCD for A and B, if I have to write the formula for that, I call myself with B and A mod B mod A, and we just assume that it'll work, that GCD works correctly. Recursion is not easy. You have to practice it a little bit. We will have a tutorial this afternoon to try and practice recursion, but it's a tricky concept. I'll admit that, and don't feel bad if you don't get it at once. Okay, it's now 8:30 and I'm going to stop and I'll answer questions if any have popped up. A couple. Oops. Yeah, when I am in presenting mode, I don't see the chat or the I can't see my little microphone. It's very tiny on the screen. Okay, can anyone else hear Yaku? No, he couldn't, and I was muted, and I didn't mute myself, I promise you. Anybody can mute anyone in this stupid meeting. Maybe I should try to find out if I can set that. Okay, right. Was muted for the whole explanation of the code. Oh Lord. Okay, I don't know what to do about that. I will go listen back to this recording, and if a lot of it is missing, I don't want to make any promises, but I really want to record last week's lecture today, and if today's lecture is also missing a lot, I will re-record it as well. I don't think there's anything else. We will probably have a shorter tutorial this afternoon, and because we have to do some other exercise as well, an experiment this afternoon in class. But then we will start with recursion again on Monday, but this time using it for graphics. And even though recursion is a tricky topic and graphics itself is tricky, it actually makes it easier to understand recursion because you can somehow see what is going on. So hopefully that will help you a little. Raise your hand. I've never seen this little sign. What does it do? Your hand is raised. Well, I can't see that. Lower your hand. Oh. Okay, new button. Oh, somebody's raised their hand. Excellent. And now I can unmute you, and then you can ask a question. And okay, right, cool. That's good. But I'm not going to, you must ask in the chat if you really want to ask a question. Good. So, new feature in Teams. Okay, if there's nothing else, I'll still be online until 10 to 9. Then I have to go to the next class. But ask questions if you want, but not in the meeting. I'm going to leave the meeting now, so just ask in the regular channel. Okay, thanks guys. I'm going to stop recording and I'll put it on Sunday as soon as it's ready. Stop.